case you kind of lost track of what we're doing here, I first derived the sum of difference formulas using Euler's formula. Well, that was a little bit of cheating because Euler's formula requires knowledge of calculus in order to justify it. So then I turned to the geometric way and finally came up with this cosine identity, cosine alpha plus beta. And without going to Euler's formula, I want to know what's the sine of alpha plus beta. And this is what I need. I need these transformations here. So in thinking about this, I'm going to keep alpha the same, and I want to change cosine beta and sine beta. I want to turn this into a sine. All right. Now to do that, the sine of, take this, the sine of beta would be the cosine of beta minus pi over 2. All right, so that's my trick here. I'm going to let beta. I'm going to replace beta with beta minus 2. So I'm going to replace, and I'm not going to change it, use a different variable this time. I'm just going to replace beta with beta minus pi over 2. And we'll see how it happens. Now, it's going to work out nicely here. A little worried about that, but I think this is going to work out fine. So I have the cosine of alpha plus beta minus pi over 2 equals cosine alpha cosine beta minus pi over 2 minus sine alpha sine beta minus pi over 2. All right, so let's see if this helps. Now here, if you rethink the first one and see it as alpha plus beta minus 2, I have the cosine of an angle minus pi over 2. Cosine angle minus pi over 2. That equals to the sine of the angle. And what I'm referring to as the angle is alpha plus beta. So for this identity, pretend theta is alpha plus beta, and it works out very nicely. We get this turns into a sine function. It's a phase shift to the right. So we have the sine of alpha plus beta. All right, that's what we wanted, because we wanted an identity for sine alpha plus beta. Now over here, cosine beta minus 2 is sine of beta. So I have cosine alpha sine beta. So far so good. Minus sine alpha. Now what's the sine of beta minus 2? I don't have an identity for that one, do I? Let's see here. So what am I going to do with that? Sine of beta minus 2. Well, let's see. If I take the hang on, I'm drawing a blank. I'm going to pause for a second while I think this through. Okay, I figured out my conundrum here. I didn't want you to have to sit there and watch me think this through for a minute or so. I do these videos pretty much on the fly without a great deal of preparation, so once in a while I run to a little snag like this, but I think I know what to do. Alright, now we want to look at what does this mean? Okay, that's taking the sine function. Alright, so here's the sine function. So bear with me. I'm going to draw another graph. And this sine function, hang on, this is just the sine of theta. Okay, it has. Alright, now if well, let me call this sine beta. I mean, this is beta up here, so this is y equals to sine beta. Alright, great. Now, if I replace beta with beta minus 2, then I get this graph. So that shifts it to the right by pi over 2 units. I wonder if you can see what's coming here. It's a little tricky. And yeah, I had to think my way through this. Alright, so the green graph is y equals sine beta minus pi over 2. Now, how does that relate to cosine? You see, cosine, the red graph, okay, goes like this, and And this is getting kind of cluttered. Alright. And reminds me of how electricity is generated in electrical plants. 3 phases, 110 volts, 60 hertz. Okay. That's how the electricity is generated, I think, by the big turbines. There are actually 3 sine waves representing voltages. But that has nothing to do with this problem. The red graph is the simple cosine function, cosine of beta. Well, look at this. If I reflect it across the x-axis, then I've got this function. So these two are quite related. One is upside down from the other. That's a vertical reflection. If you change all the y values, then this sine, beta minus 2, will turn into actually the negative of cosine beta. Well, it equals to cosine beta. So, but if I reflect it, then what I'm getting is over here basically minus cosine beta. All right, because the green function is the negative of the red function. All the y values have switched, flip-flop. How about that? So I got to use another function transformation from a college algebra class. Can I erase this? I suppose I can. Alright, so I think we're done. Because now all I have to do is just rewrite this, and we have the sum and difference formula for sine. So we'll write that and take our victory lap, and then we talk about it a minute and admire it, and then move on for some applications. So finally we have sine alpha plus beta is the cosine of alpha, sine of beta, 2 negatives cancel, plus sine alpha cosine beta, which squares with the identity that we derived using Euler's formula. So there we go. So I had these 2 basic formulas, which I was able to get much quicker by cheating with Euler's formula. But with these 2, then using the techniques in that earlier video, we can go ahead and get cosine alpha minus beta, sine alpha minus beta. We can get the tangents, and from there, secant, cosecant, and cotangent. So I think we've succeeded in doing the sum and difference formulas by two different methods, and I hope you learned a lot from it, because there's some really interesting ideas, I think, in coming up with this. So okay, let's move on to some great applications.